Okay, so welcome everybody. Today we have session 21 on plane strain. But before we do a little bit of a discussion on plane strain, just like to point out something that came up in the chat about this problem. I don't know if you recall, but we've had multiple things in the group me about the spherical pressure vessel. Okay, and what is the max shear? The max in-plane shear is 0, okay? And that's what we've been asking, right? And we said how it's a dot, okay? But after our discussion yesterday, right, the out-of-plane absolute max shear is not 0, okay? And I wanted to point that out because I think I glossed over that a little bit too quickly. Because I got excited, right? It's a dot. It is for in-plane, right? But what do we need to do, right? If we're looking at, so this is absolutely the case. Very true for in-plane Mohr's circle, okay? And if you look at exam 2 from the spring, we actually, unfortunately, we divided the Mohr circle on stress into 2 pieces. And wow, I believe we did cover absolute maximum shear stress right before the exam. I said you're not responsible for it on exam 2. This time you are responsible for it for exam 2, okay? So if you look at, I believe, the second question on exam, actually I can show you. Whoops, I didn't want to show that. Okay, so let's see here. So if you look at this exam, excuse me. Okay. And look, it's the same thing. Sigma and sigma. That's what you have with a spherical pressure vessel, right? It's PR over 2T for the sigmas. Okay, and in that case we said, okay, look, you've got to use the triangle. We asked people to use using equilibrium on an appropriate triangle, right? So you have to be able to do that. Okay, and then we said, draw an appropriate Mohr circle, okay? And what is the maximum in-plane shear stress in the XY plane? Very specific, okay? So that's truth, okay? Then the next session essentially after this exam, or the first session that was covered on the final exam, right, was absolute maximum shear stress. So this is very true for in-plane Mohr circle. But as we now know, if we're looking at absolute maximum shear stress, okay, we often have to look at what the out-of-plane normal stress is. So in this case, what is the sigma 3? And the sigma 3 is 0. Okay, so if I draw the Mohr's circle, just like we have here, okay, that's still truth, right? But what we have is one additional circle that we draw, because this sigma 3 is equal to 0 right there. Okay, that's sigma 3, and this was the sigma 1 and sigma 2 over here. So now if we look at the absolute maximum shear stress, we're looking at the radius of this circle. And what's the radius? Well, there are a couple of different ways to figure it out, okay? But essentially the radius is going to be equal to that sigma 1 or sigma 2, right? Which is just, in this case, the sigma 2. Okay, that we had described all the way back up here, or all the way right here. Either way, right? So that means that the tau absolute max is going to be equal to this sigma 2. Sorry, guys. Right, it's just sigma 2 over 2. Okay, so that in this case that would be PR over 4T. Okay, so I just wanted to clarify that, and thank you for participating in the group. Julio sent a nice screenshot. And so as you find these other resources, if they're not already linked to the website, right? If we don't already have links, let's send them, and we can put them on there. All right. Say, I think this would be a good one that we should include. Okay. Now, session 21, as we see here, okay, is about plane strain. So, plane strain is similar to plane stress, right? Where we're looking at situations where it's a 2D perspective, right? And we're trying to think about what is happening in terms of the normal behavior, right? Coming out of the sides, and also what's happening in terms of the shear behavior. What's a little bit different here is that we are looking at typically pieces of a material that are thick. Okay, now that's something that doesn't come out too much in what we're doing here with the work, but it's something to keep in mind, all right? Because we're going to look at strain gauges. We're going to kind of make some equations where we go between plane stress and plane strain. We're not super careful, but the general idea is that this is kind of a thicker sheet, but we're looking at uniform strain across that thickness, and that is the plane that we're dealing with. Something else to consider is that we've already described situations where we relate the stresses to the strains, okay? And when we were doing it with the stresses by themselves, we don't think not too much about the Poisson ratio. That's not completely true, because we have our tau is equal to G gamma, okay? And G has dependence, the shear modulus has dependence on the Poisson ratio, okay? And we've kind of just given that to us, right? We said G is equal to E over quantity 2 times quantity 1 plus nu. Actually comes up again in this session. But something to keep in mind is that when we're looking at just the normal strains, we do have this dependence on stresses in the orthogonal directions, okay, through the Poisson ratio. Another thing to keep in mind is that when we've discussed shear strain in the past, this is the picture that we've typically used, where we said we had a gamma angle, which was dependent on how much lateral shift there was over the distance, the vertical distance. Kind of like what you have with, well, shear stress in a Newtonian fluid, okay? It's pretty similar. In mechanics, another way to look at this is to think about these shapes or these deformations resulting in something where the bottom piece is not necessarily horizontal, okay, but it can actually distort in a way that you have the rhombus having angles on an angle away from the horizontal axis, okay? And if all things are the same, then what we actually have here is a gamma over 2 and a gamma over 2 here, okay? Instead of just a gamma like you have here. Another thing that works itself out in the math is that the plane strain transformation equations, okay, so maybe I should back up. Just like we can take an element and rotate it and then calculate the new state of stress, we can do the same thing with the strains. Okay? And if you remember when we were doing the finite element analysis at pre-Pomax, we were talking about the Cauchy tensor, and we were talking about how sometimes, or a lot of times, when you write out the tensor or the matrix, all right, but the tensor for the strains, that tensor is filled with gammas over 2, okay? And that works itself out in the math. If you want to look, in Hibbeler's book, you can. If you want to look at this handout online, you can see the derivation. But what's kind of interesting is that when we do these strain transformation equations, yes, there are these quantities like average and the difference over 2. Those are not too distinct from what you saw with the stress transformation equations. But what is kind of distinct is that for the shear strain, we have a factor of 2 often involved, okay? And that is something that we want to keep in mind and be careful about. These equations, as far as I know, are correct. So these circles of nothingness are just to point out that you need to be careful. We need to be careful, okay? But at least careful in terms of what you would see with the plane stress equations. All right. Now, just like we can do Mohr circle with a plane stress situation, we can do Mohr circle with plane strain. And the thing that is most different, okay, is now that the vertical axis, instead of it being tau, is actually gamma xy over 2. Okay, so, and you saw in the strain transformation equations, right, we had this new gamma xy over 2 that we had to be careful about. So, this is now the second kind of thing that can be confusing, because we have a 2 theta already, okay, in our Mohr circle. So 90 degrees on Mohr circle, right, corresponds to the element rotating 45 degrees. And now what we're saying is that the gamma xy over 2 is what we have in the vertical direction. Okay, so when we look at maximum shear strain, we are going to get a number, the radius, right, that is actually gamma over 2 instead of just what the in-plane maximum shear strain would be. Okay. So those are 2/3 of what this session covers. The last part is, I think, a nice practical addition to our understanding, and that is some information about how you go about measuring strain on an object. So there are situations where you can't stick it in a tensile testing machine. All right, and so and maybe it's a pressure vessel even. Okay, and you would like to be able to monitor how it's doing, what the relationships are between, say, the internal pressure in the vessel and what the deformation might be. So what we can actually do is stick a wire on the thing that's being stretched. And this is a strain gauge, and it goes back and forth. And we can look at the change in that electrical resistance as it is strained, and then relate that change in impedance, electrical impedance, to the change in strain. Okay, and it, in one respect, okay, electrical resistance, I think, oh, this is really cool. I remember back from my equations, if I had a wire, I can think about how the resistivity rho, the length, and the area, the cross-sectional area, related to the electrical resistance of that wire. And that is true, right? If I pull a wire, or if I have a hose, right, with liquid going through it, you've probably heard this analogy before. Hose, water is going through it. If I pinch that hose, or I make that diameter smaller, it's going to require more pressure to get the same amount of flow, right? So that's the same thing that we're talking about with charge. It turns out that it's not just about the change in cross-sectional diameter with the materials that are typically chosen for this. You get increased sensitivity from a piezoresistive effect, so that the resistance actually changes. The strain actually induces a higher change than just the cross-sectional area changing. Either way, what's really nice is that we have devices that are not incredibly expensive, okay, that you can attach to a pressure gauge, or attach to a pressure vessel or some other object, to be able to figure out how much strain is undergoing. The attachment of these gauges, now this is just more practical information, but the attachment of these gauges is not trivial. You need to have very good contact between them, and the strains that you measure can be very, very small. And you've already seen in the problems, often we're talking about microstrain, tens of microstrain, okay, hundreds of microstrain. So if you don't have very good intimate adhesive contact between your strain gauge, if they're slipping relative to each other, then you're going to have issues. So when you shop different websites for strain gauges, don't just buy the strain gauge. Look to see which adhesive they recommend as well. Okay, so you can, yes?
The adhesive limit the straining of the material?
Sure, yes. I mean, if you had a really thick, like imagine that the elastic modulus of your adhesive was super high, right? And it was super thick. You could imagine, or actually you could imagine if it's super low, okay? That probably is a better situation. Like if I put a strain gauge on a piece of rubber, right, and something strains underneath it, then I'm going to have no ability to measure what the strain is above, right? So you want to have really good intimate contact, and yes, almost like rigid contact, so actually very high elastic modulus if possible, so that the strain gauge feels that strain that the object is feeling. Yes, Michael?
If the material was conductive, could you just send electricity through it itself and measure the change in resistance?
Okay, so again, so yes, theoretically, okay, what's happening here is, again, there's a piezoresistive effect on top of the electrical effect that you have just with the resistivity, and you see that this thing goes back and forth a number of times, okay, so that you can, because if I just have one length, so essentially this is trying to multiply the effect, okay? So theoretically, yes, but you're gonna have a lot of noise probably, electrical noise in that type of system, but it's an interesting idea. There are other methods, there are other techniques that people use for measuring strain. And there are image-based techniques. So there's something called digital image correlation, which is this technique where you have a lot of dots, and then you have a camera, and it's actually able to measure the relative motion of those dots. You have you have acoustic methods as well, okay, and those techniques can be effective at measuring how much tension is in play too. And I mean, there are different behaviors in how sound travels through objects, okay, based on bulk modulus, density, right? Bulk modulus, they're related to each other when it comes to figuring out how fast sound travels. I mean, even things like audible acoustics, we know that when we tune strings, right? As you change the tension in the string, you're going to have a very different audible characteristic, right? And that's also a measure of strain. Okay, so the point here, though, is that we have a technique for measuring strain, but it's not always that simple. In that, if you only care about strain in one direction, great. But as we've discussed, right, we often care about strain in a couple directions. And we may want sigma, or we may want epsilon 1, epsilon 2, or we may want epsilon x, epsilon y, we may want a shear strain as well. So what happens is these strain gauges are typically, they're put, well, if you just care about uniaxial strain, just use one, okay? But if you care about getting the epsilons and the gamma, right, where we have 3 parameters, then we want to use 3 strain gauges, and they are put at angles relative to each other. Okay? The simpler one is this one, where you have them at 45 degrees, but you can also do 60 degrees between them as well. And so for this, we can use the strain transformation equations that we've been discussing previously to relate strain measured in one axis, okay, to strain measured in other axes as well. And so there are derivations, okay, for the for these different situations, and so these are strain gauges 60 degrees apart from each other, and then this is rectangular. These are 45 degrees, and it's much simpler if they're 45 degrees apart. Okay, great. So take some time, go through the videos, ask some questions. I expect, though, most of you are studying for tomorrow's exam, so ask questions. You know, let's be smart. Let's ask questions about what's happening tomorrow. Okay, but let's ask questions about these two. All right, and I'll be around. The exam tomorrow, same thing that we had last time. Right here, same amount of time. I expect about similar number of questions. No guarantee on that, but about that. And then you can bring 2 sheets of notes instead of 1. Okay. And a calculator. Bring a calculator as well. All right. Good. Have at it. Just gonna stop this for a second.
Did you do Q6?
on which way we're doing the cut, right? But if, you know, typically, right, we have our nomenclature, right? That if we expose the right, we have our convention where it's going down. If we expose the left, then we have it going up.
So
I did exactly.
you can choose either exposing the left or the right. So if I choose exposing like cutting from the other side, and the edge will be pointing the other way.
So there's a difference between this and this, right? This is I mean, first when we talk about convention, right? First we're talking about the convention for the shear force across the beam, right? So we had to get that convention right. But then, yes, if I take an element, right, where I've got that convention going, and that element has a face like this face, right up to it, yeah, the internal shear force is going to be the same. Acting over that area, so then I can figure out what the stress would be.
So if I draw, let's say the arrows to be like a positive up, the positive shear stress up, then the cut should be done exposing to that side.
So if say that again. So yeah, so if you take a cut going the other direction, right, then it's going to end up on the other side.
Yeah, these gonna end up going downward, right? The positive edge.
Well, but see, it depends on how you define x, right?
Yeah, because here's defined like going outwards. This is the beam, this is the wall, so edge is here, right?
Mm-hmm.
So if I cut through here,
Mm-hmm.
then the positive shear will be going down.
Mm-hmm.
Right.
So if, as long as I'm exposing that right
If
side.
I close on this side,
yeah.
and the normal force will be going out.
Yes, that's right.
Okay, that's this case, right? So if I expose the other side, if I cut here, I expose this side,
Right.
then if I want to draw this, I will have to draw this positive edge to the other side.
Well, that's actually negative x. It's still in tension, but it's going to be an x in the opposite direction. It's actually a negative x space.
Okay.
If I use this one, right? It turns out for tension, it doesn't really change anything, right? But it does. But if you're looking at shear stresses, right? Like we've talked about in the past, that can change things, right? Because look, if you're on the positive x space or on the negative x space, it changes which direction is positive for the shear stress. Does that make sense? Right?
Yeah, because then it will be rotating if I use the same
Yes.
convention.
Yeah.
So as long as they balance and I get right with the convention,
Right.
it'll be good.
Right. And what's also confusing, right, is remember that when you have the face, I mean, maybe
I said my work was unclear.
so there's a question just about the convention that we often use. Okay, so if we have a beam, right, and we take a cut, okay, we have to be very careful, right, that we use the appropriate convention here, right? And if I instead took the cut this way, right, then I would have like that, right? Now the question though, right, is that in both cases, that's the x direction, right? At least if I'm thinking, right? right? So then when if I draw now a stress element, right up to it, correct? This is where we get into some interesting stuff. So we take a stress element, okay, and let's just say that that's x and y is this way, right? So that z is coming out at us. Let's just say that, right? So in this case, yeah, I'm going to be thinking about what is how's that force, right? Shear force affecting this this element, right? And this is going to be confusing, right? Because I've got if I had I had this shear force V, right? But if I'm defining my positive, right? I would still define my stress state like that. Okay. Like this is one convention, right? This is one convention that I had to use on this as well.
So if the shear force was like up, like negative, then you will use down in the element. Okay.
Yeah. Okay. And then here, right? I get this other element over here, right? And this one, right? If I follow my convention, here, right? I've got to keep track of this shear force like that, but I still have these to be concerned about. Okay, and they're on opposite faces. Look, this is in the opposite direction of this. This is in the opposite direction of this. Everything's fine. Everything's fine. Everything's confusing, but everything's fine.
Why is it going down there in the right? Like it's positive.
Which one? Why is this going down?
Yeah, so that's supposed to be like the.
Well, if I'm still using this reference frame over here, right? If I'm still using this reference frame, where this is x, and this is y, right? I'm still using this reference frame, then this is how I draw the element. These are the defaults. This would be a positive, right? This is the positive tau xy. This is still a positive tau xy. This v is equal to this v, okay? And if v were positive in this case and v were positive in this case, right? In both cases, tau xy would end up being negative.
So it doesn't matter like it, because in that one it seems that B is in the right of the box and then the other one is on the left. Of the
Right.
It doesn't matter, right? It's
Well, it matters how I define things, right? It matters. I mean, if you wanna draw an x coming out of this face, okay, you could do that. That'd be fine.
it will be the same thing.
Yeah.
I just changed the convention. Okay.
Yeah. Yeah. A lot of this stuff is just based on conventions. Good.
Right.
Good. Well, so I mean, if we go all the way back. Right. I mean, these have been the conventions that we've had for a while. Okay. and so it's where's the yeah, I mean it is confusing because even CDL and Hibbler, right, they have chosen to use different conventions. And yes, this can be confusing here too, right? Because sometimes we say we have X coming out, right? So if we choose X coming out, then yeah, it'll be then in that case it would end up with the opposite of what we're discussing. Okay, were there other questions? Yes.
I was going to get calculate amount certificates, we can't choose the result, right?
Okay, so you calculate what?
From like a.
Yeah.
You just use the resultant.
Yes, you can use the effective resultant, okay? You need to figure out, we need to know what the distance is at, right? So this problem, so Michael is bringing up this problem. Okay, so in this case, there are a couple ways to attack this problem, okay? We can always use equilibrium, right? This beam problem, you could have solved for the internal shear forces and bending moments back using what you knew in statics, right? So that's fine, and the simplest technique there, all right, to figure this out is to go ahead, take a slice, all right, and in this case, define a parameter from the right side. Maybe we call it D, okay? And now, again, we're using our conventions. Let's use maybe that color, I don't know. So we have a V, and we have our internal, these are internal M and V, okay? And now there's external. Distributed force, right? And maybe we say that this has some constant W naught. Okay. So if that's the case, right? If I want to do equilibrium, let's use a different color. And then we'll say vertical direction equals 0. Then what I can say is, well, V minus W naught times D is equal to 0. So the internal force, V, internal shear force, is just W naught D, okay? Notice the distance, I mean, maybe I should have drawn D a little bit more clearly. So like D is actually coming out to this location, right? So if I'm really close to the end, actually, you tell me, what's the shear force, internal shear force right here at this point, at the end? Internal shear force. 0, right? Okay, and then if I were, if this distance were A, right, then we could figure out, okay, right up here, right around here, we can figure out what the shear force is. It's just going to be W naught A. Okay, now if we're doing the moments, right, we have to be a little bit more careful. because we have to pick a location. Let's pick at open face, because then we don't have to substitute v, right? That's a common thing. Maybe not always the best, but sure. So at face, that has to be equal to 0. So in that case, okay, we've got what we'll call a negative m, and we've got now also a negative, okay, contribution from where is this effectively acting? This is effectively acting, right, at the midpoint. So it's going to be acting at d over 2, and it's going to be having a magnitude of w naught d. So when we do this all out, m is just going to be equal to like that. Does that make sense?
Yes.
Okay. Now, let's just say if this were, if this were a situation where we had a distributed load like this. And this is kind of a review from statics. Okay. This is kind of unpleasant, quite frankly. Okay. Let's just say this is W max. There are a couple ways to do this, all right? One is, there were a couple ways to do the prior one too, right? But this is not super fun, okay? But if we just use equilibrium, we forget what we know about integrating, okay? If we just use equilibrium, then we can say, all right, first external equilibrium. That's our first thing. And we need to know what we're doing with the vertical forces, right? They have to be equal to 0. And so if we think about this, right, we've got the opportunity to choose whatever reaction, force, and moment we want. Okay, and the convention does not apply. In this case, pick what you think is logically happening. Okay, think about what's logically happening. So in this case, right, first we've got to figure out what that net force is, right? And so that's going to be just 1/2 times that, right? Because if this were a rectangle, right, then it would be W naught, or the W max, times that that length, right? So if this has got some length L, then we can say that the vertical, so RL we'll say is positive, minus 1/2 W max times L equals 0. So RL is going to be equal to 1/2 W max L. Then also using external equilibrium, we're going to look at what's happening with the moments. And in this case, let's go ahead and let's pick at the left side. And we always have to pick a location that has to be equal to 0. So now I've got a situation where ML, okay, and then minus, so ML is a positive moment on the structure, and I've got minus, what's happening here? Well, this is happening 2/3, the effective force is 2/3 away, right? So that's happening 2/3 down the line. Okay, so it's going to be 2/3 L. And what's the effective force? 1/2. Like that. Okay, so that means that ML is going to be 1/3 W max L squared. Okay, and so that's just doing the external equilibrium. Now we want to do the internal equilibrium. Okay. What am I doing? What am I doing? Okay. So we got to take a cut, right? So if we take a cut, probably easier to do it this way. So now we've got X like this, we've got our distributed load also being cut, all right, and we have our external forces at the end. So we have our RL and we have our ML. Okay. So here again we can figure out what the, so this is for internal. Here we can say, well, some in the vertical direction. So we have our RL, which is positive. We have our minus, what the length is, right? So this is going to be 1/2, what the length times the distributed force is. So that's just 1/2 the max. All right, X in this case, because X goes to this edge. All right, so then, and of course, we have to make sure that we have our force, internal force in our moment. That will make things tricky. Okay, so that's going to be minus V is equal to 0. So V is equal to the RL, which we calculated previously. So RL, I'll just write it out. RL minus 1/2 W max L, and that is RL is 1/2 max W max L, so that's going to be just the 1/2 W max L minus X. And for the moments, let's do moments, well, this time we'll do the moments at the right side. Okay, set them equal to 0, so we're here. So M is positive, so we have positive M. we have no contribution from V, we have a positive ML, okay? And we also have a positive contribution from this distributed force. And where is this distributed force acting? Well, it's acting, again, effectively here. So now it's 1/3 from this side. Okay, so it's 1/3 L. And what's its magnitude? Well, it's, 1/3 X. And what's its magnitude? 1/2 max X, right? And this is going to be equal to 0. So in this case, what we have is M is equal to minus ML minus 1/6 W max X squared. Okay, and what was ML? ML was 1/3 W max L squared. Okay, so we can write this a couple of different ways, but one way to write it would be as follows: minus 1/3 W max L squared plus 1/2 X squared. Did I do the math right? Any issues? So that's maybe a little bit of a review from statics. Did I do something wrong?
No, I have a question. Like, if
Yeah.
do I have to if there is a way that I can solve without having to do cuts, do I still get credit? Full credit? Because
It depends. Okay, so there's another method, right? There's another method, which is the graphical method and the integral method, right, that we've talked about, which could potentially be easier. Okay, so for example, maybe we should just review that because that is fair game. Okay, let's do it on a simpler one. Okay, let's do it on a beam that has a distributed load, but it's constant. Okay, so now if we use the integral technique, right? What's the integral technique? Well, it comes back to the two equations, right? That the derivative of the shear force with respect to x is equal to an external load, distributed load. And it comes back down to dm dx is equal to the shear force, right? So this is definitely fair game because we covered this previously. Okay, so in order to use this technique, though, we need to do the boundary conditions, right? Matt, you were talking yesterday about differential equations.
Yes.
And what is one of the things you have to do in differential equations? You have to figure out what the boundary conditions are, right? To, like, if you have a non-homogeneous problem or something, right? And it's a pain, right? You have to guess what the form is. Okay, this is not the same thing, but it's kind of similar, right? So here, what are we going to do? Well, first we're going to do. You always want to do external equilibrium first. Okay, for both techniques, right? So external equilibrium first. Okay. So for this, right, I'm going to go ahead and draw the beam again. And I have two conditions, right, or two constraints really here. I have a vertical one and the force. And I get to choose. When it's reaction forces, I don't care about conventions, okay? I just care about trying to pick, and sometimes you don't know, but I try to pick what makes the most sense. So I'm gonna pick this as my RL, and I'm gonna pick this as my ML, okay? And I've got this distributed force. That's coming. All right. So when I'm doing the external equilibrium, right, RL is going to be equal to whatever this is W, this is L, right? It's just going to be equal to WL. And when I do my ML, okay, that's positive, all right, and then I got minus the 1/2 L times the WL, okay, so ML is going to be equal to 1/2 WL squared, okay. So now we've done external equilibrium. That was pretty painless, not too bad. If we use the integral technique, all right, on these equations, what we need to do is we need to figure out what the boundary conditions are. So we do left side. All right. Isn't there some movie? Left side, right side. No. Nothing.
The blind side?
Blind side. I don't know. Okay.
No, it was a movie in the 60s.
Okay.
Yeah, there you go.
Remember the Titans? That's not from the 60s, is it? That's okay. That's like Denzel Washington or
No, I'm
something?
saying like it was set like back then.
Oh, okay. All right. All right. So anyway, left side, what we need to figure out is what's happening internally there. Okay, and so what's cool is like you say the distance is really small, so the distributed force has no contribution here to this calculation for the boundary conditions. So on the left side, what you do is you say, okay, V is got to be equal to R. You see that? They balance out. And you say that M has to be equal to minus ML. That's not so nice, but that's how it goes. Okay? The right side, we draw this out and we follow the convention. As we see here. And we have V equal 0. And what do we have M equal to? 0. Okay, so that's good. Now, if we draw the plots, so we start plotting. We'll do the shear force one, like this. Okay. And let's do the, whoops. So this will be shear force. This will be moment. Okay. What do we see here? We see that if I put L and L here, we have 2 points on each of them now. We know that we have to end at 0 for both. Okay. And we know that on the left side, we have V equals R. So R was just WL. And here we have minus ml, so we're down at 1/2 minus 1/2 w squared, wl squared. All right. So the question is, how do we get from these 2 points? And that's where we have to use these equations, right? So the first one, we have that dv dx is equal to f. We can say that integral of dv is equal to integral of f dx. Okay, this is minus w, right? By the convention. So we get that v is equal to minus w x plus c1. All right. Well, there are a couple ways to look at this, but if we start where we said this is x, right? Then when x is equal to 0, c1 has to be equal to wl. So c1 is going to be equal to wl. And so this expression is going to be v is equal to w l minus x. Okay, and so that allows us then to draw a straight line just like that. Okay. And then if we want to do the one over here, all right, we have to use another equation. We use that dm, I'll change colors to make it a little bit more appealing. dm dx is equal to v. Okay, so that means that we can do integral dm is equal to integral v dx. Okay. And so what do we get? We get m is going to be equal to what this integral right here, right? So we're going to integrate, okay, this wl minus x, okay, with respect to x, and we can, it's an indefinite integral. So when we do that, what do we get? We get wlx minus 1/2 wx squared, and we're going to say plus a c2. Well, there are a couple ways to do this, okay? But again, maybe the easier one is when x is equal to 0, we have that this has got to equal to minus 1/2 wl squared. So that means that c2 like that. So that means that this moment equation is going to be wlx minus 1/2 wx squared minus 1/2 wl squared. Okay. So I guess there are a couple ways to break this down. We can take the w's out from everything, okay, if we want. Okay, and we can I guess let's just write it like this. All right, lx minus okay. what is this expression? This is a second order polynomial. It's a quadratic, right? And is it opening up or down? It's opening down, opening down, right? So it's a second order polynomial opening down, all right? And it turns out, right, that this would correspond to when it hits the
Zero,
the zero, right? So, you know, what we get to do here is essentially just draw a second order polynomial, a parabola of sorts that goes through. That's not the best parabola, but that's something that has some curvature to it, like that.
So
Okay.
we did like all the integration just to figure out the shape.
So, if we don't ask for an exact expression, then you ought to be able to just say,
Yeah.
I'm integrating a first order line,
So then I get.
a first order polynomial. If I integrate it, it's going to become a second order, okay? And so that would be fine. If we say we want the exact expression, then you need to do the integration,
Okay.
right? I mean, that's just how you have to do it. Good.
Okay. So if you don't ask for an expression, then you just.
Then just draw it.
You just
Yes,
draw it,
let's
right?
draw it. Let's draw it, right? Yeah. Now, there are a couple things to point out. I think you're getting at, Carlos. If the question is, where is the maximum bending stress?
Wait.
I don't have to do a whole lot, right? No,
It's
because
just
like
the-
you just said, it's just right
It's
here.
that, right there.
It's right here. So I solved it way back over here when I
So-
figured out
so
what the
if
internal.
That's the question that I don't have to go through everything,
No.
right?
If you want to know where's the maximum transverse shear stress, again, left side, right?
Section 10 is on the exam, right? Where is it?
So we, I mean, it is on the exam because we have combined loading, right?
Okay.
Right. So you have to be able to do calculate out
Yeah.
the shear stress. Yeah. Okay. Yeah. But well, I don't know if I should say anything. And you know, session 10 also emphasized indeterminacy and also emphasize angle twist. Okay. Yeah. We're focusing mostly, I mean, it's possible, but we're focusing more on the stresses in this part of the class. Okay. Now, do you need to know how to use compatibility to figure out stresses sometimes? Absolutely, because you can't figure out what the internal moments or the forces might be if you have an overconstrained problem. Good. And if I made any mistakes here in my math, please let me know. And also, you're still responsible for doing it correctly on the exam, even if I made a mistake here. Because this was just off the top of my head. I wasn't going off the notes here.
Also, like to do like the bending moment diagram, can I just like look at the area of the shear force and then just do like the different like the changing moment and then just 2 points and look at what type of curve is it? Because
Sure.
that way I don't have to like derive another equation for bending moment and I'll be like,
So, I mean, an integral is the area,
yeah, so
Right.
maybe like
right? Right. This is an expression, right, that's helping us understand the area under the curve.
so if it doesn't ask it specifically for an expression, I don't have to derive it. Okay.
Yes.
That's
Right.
my only concern.
Right. And if it asks for a maximum,
Very much. So yeah, it's just
you know, yeah. But we did have that kind of brutal question, right, where we had MAP and FAP, right? Do you remember that across the beam? We had MAP and FAP, and then you got like a maximum kind of not at the ends.
Yeah, it's when it crosses sometimes.
Yeah,
You have to look at
yeah.
the maximum there.
Good, 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 good. Okay. Okay, we need to take attendance. Yes.
I was looking at the combined load
Yes.
slides, and then right here you said there's no bending stress from PY
Yes.
because A is on a neutral axis.
Right.
Why is that?
Okay, well, what is the expression for bending stress?
Isn't it just P times?
No, just what's the equation? Just what's the equation for bending stress?
2 4
It's the Fletcher formula.
Sorry, I'm drawing a blank. For some distance.
My over I,
Oh, yeah, MY over I.
right? Okay, or negative my over I.
Yeah.
Okay. So
No, that's in.
what we're getting at here, right, is that since if you have a point on the neutral axis, what is the water?
I have
You don't know how to break into
Right.
So just like on any axis or both for
It's specifically for that. So if you have bending about the Z, so let's say we have a bending moment, right, which is what PY is doing, right? The effective length of action is A, right? So you have this PYA,
Yeah.
right? And that axis, right, is Z, right? That's what it's bending about. For that beam, A is on the neutral axis.
Or you only have just that.
You get it?
Oh, yeah, yeah.
You see what you see? Right, so
that's
since
the
it's on the
maximum.
neutral axis, y is equal to 0,
So that's the maximum
then
value.
then each stress is 0.
You do
So like-
x, y, y, and x, y, y,
If A was like rotated like 90 degrees.
No, so-
Then, yeah, then you have the stress.
Oh,
and
okay.
g
You
zero.
would have the
So
neutral
you
axis.
have 0. One is,
And
it's
also
on the biggest
one
circle.
thing,
The bigger radius is-
to get tau x, y,
and the x, y.
you just,
Yeah.
so for a negative portion, sure.
It's three things right there. One of them is zero.
Because
Zero.
it's like rotating this way, right? At that point,
Right,
Yes.
that's right.
so then if A was like here, it would be positive.
Yes, oh, well, so if A were up here, would A was, on the right side? Yeah, because the opposite direction.
Alright, got it.
The opposite direction. That's correct. And it's confusing to figure out which coordinate is which, right, in terms of how it's being defined. So, right? And so, you know, if you draw the element and, you've got, the XY face, right? Or the XY plane, and you're looking at the X space, right? Yeah, it can be,
Also, basically, circle,
Good question.
x and y, y and z is second check.
There's a permission from McDonald's. They're shrinking it like percentage of that.
Basically, that's there, that's there.
The what?
Just please ignore it.
Okay, how
It's not even worth it. You're just gonna think lower of me.
So this is clearly, one back to that is very certain.
Oh yeah, that's exactly like cuts to that at the end. Yeah, like dead. Yeah, but it's not real. They just like. I think it's so.
Well, no.
It's just stupid.
It's so
funny. Like, have you seen the guys who like do it and they like go off?
Yeah, no, this,
And
what
it's
right
just
there.
like they look at this and it's just like. I get secondhand embarrassment. Oh.
That's what you're doing earlier, so it's gonna be the small stress plus the big stress, value two.
Yeah, some of them, a couple of them are so,
Well made.
dude, they all got like 6 good content points.
Oh, maybe that's throwing me off. Like I know this is the.
Yeah, I mean, to be honest, in the sense, I did, with that formation, you don't need to throw this stuff. You take the biggest mix of small, value two, and big mix.
Okay, thank you.
I mean, if it's more complicated than that, then if I wonder, I mean, if there's no shear stresses, and just, normal, that should be good enough. Although, has to do with the check, but, yeah.
He said that the reason
Okay.
you know J and I
Uh-huh,
is something was pirate too. He said the reason
Question.
is because he first of all he drew the J like this. He drew the J like this. And the I like this. And he said the reason it's pi over 2 from the J, pi over 4 from the I is because
Wait, I don't hear this.
the J has 2 points and the I has 4 points. Like, you want me to show you? The J has 3 points. Well, that's what I'm saying, but he just drew it wrong.
So the way I remember it
Yeah.
is
Oh,
I becomes
I
3/4.
equals 4J,
J.
it's pi over 4, pi over, yeah.
Yeah,
That's what I was thinking as he was explaining it. I was like,
That's how I remember it, but yes.
That makes a lot more
Let's put this
sense.
simply.
Yes.
I mean, so we're gonna, what's the sigma and tau, what's x, y, what's x, d, x, so on, so on. Meaning, so you have, there's MC, the MC of Ryan, CC of J. So, what's the, component vector? What's the difference between a moment vector?
Oh, just a way to remember
They are
that
both
J is pi
kind
over
of the
2
same
and I is
thing,
pi
but
over 4.
torque is applying a twisting, which we associate with
I
the shear
equals 4
stress.
J,
And a moment is applying
pi over 4 is smaller than
a,
pi over 2. That's why.
a bending moment, which we associate
Essentially, it's
with
the-
normal stress.
So it's either VR, C, so T is VR, and M is a definite, makes sense.
It did, say that again?
So T is V times R, and M is F times R. Does that make sense?
How is what?
No, torque, not half, T.
Torque, they're both, they have the same units. It's
Right,
both
yeah.
a force times
Yeah.
distance.
One's shear force, one's normal force. Is that right?
Why did you say that?
Uh,
I was like a serious
so-
blast. Dude, would have, if I gave you my wrist.
no.
Okay. Okay, nice.
No, I mean,
It's funny that it's never been touched before.
twisting, right, has to do with the
It's
direction
like
it's
racing. It's
affecting
like it's
on the
like-
rod or shaft versus
It's
bending. So
Like
they're
something
just
instead of
back
racing.
out to what is happening with the deformation.
It's in the
Right?
virtual.
If I take this eraser, okay, you know, and I say, okay, I'm applying a twisting force, right? And I'm putting it out here, right? I can see it's gonna cause it to twist like this, right? It's causing it to twist like that. That's definitely twisting, so that's a force acting some radial distance, which is causing that,
Yeah.
okay? But a bending, right? If I apply it, well, first if I move it over here, right? You see that this is causing this thing to bend, right? So that's not twisting, it's causing this to bend, right? So this is a bending moment, right? Being applied with this length of action, okay? Not this offset from the middle.
Yeah, it just gets more confusing when it deals with the circle.
Oh, of course, it gets quite confusing, right? So now, in that particular situation, right, what we need to do, and have you looked at the slides that explain how, like, no, not this is back in 19, yeah.
It's always been. But I'm realizing that.
No, but the
now that
geometry,
now that I'm a normal person. He's always been odd.
actually, this is going back to, no, this is back to 16, this is combined loading.
Here, still, you can have those forever.
Okay, that's great, alright.
There we go.
Right, so this is, keep going down, right? That's just the
Here
intro.
we go, okay. Yes, right.
Yes, that gives you one perspective, and then if you go down further, right, we do, you go down further, right? It's all laid out, okay? So, it's, one way to do this, and Jeff Hansen suggests this as well, is to draw a different geometry for each applied load.
Okay.
Alright, so that you can figure out what the individual contributions are of these loads, and then add them up.
Meaning, because, well, in his video, he did all three circles count each other. I guess that's probably a better way to do it, to be honest. Just do each, we can do each circle for each force on its own.
Right.
Its own.
Right.
So it's less confusing.
Right.
And then when you're doing the, into the add up the ones that are on the same, sort of, meaning, let's say, I have two moments on the same axis, you just add them together?
No.
Okay.
In this case, I mean, you can, that's fine if it turns out they're same, yeah, I mean, but I look at each load as, in this case, so in the past, right, we say, be very careful about adding stresses to each other.
Right.
Now we're gonna say, okay, if I'm sure that these stresses are in the same direction, I'm gonna add them to each other at a given location.
Yeah.
Same direction, but same at a given location, right? So in this case, I'm gonna go ahead and I'm just gonna look at what the load contributes, both shear stresses and normal stresses at the specified location in the direction.
So the sigma actually will be all the sigmas caused by and tau x.
There's not a general rule, you have to go through each one methodically.
So for sigma, so if it's caused by x, it could still be different sigma x, sigma y, sigma x. It could still be y or z. Because m,
Yeah, so-
so m, that's more confusing, right?
So
Like MC over rod, right?
again, you have to go through each one individually, right?
So
So what can I say? If you go to the very first slide, or the second or third slide in this step,
we can,
yeah, go up to the top. Go up, down, nope, next slide, that one. Look,
Yes.
these are the different types of loading, and these are the types of stresses that you can get.
Right.
This is all of them, right?
Right.
So, can a bending moment apply? So bending moment is going to be something where you get no shear
Just, yeah,
stress,
sorry.
just get sigma, right?
That's what,
Right.
that's what, yeah, sigma.
Right.
Yes.
I mean, It's true though that you can have a shear force in bending, right, due to the shear force, right, which is relevant, it's related to when we do the derivation, it's relevant to the bending moment, right? Okay, but yes, for bending, you know, for a bending moment, you're going to get a normal stress, a bending stress, okay? For a shear force, right, you have multiple ways that you get it. You can get it from transverse shear, right? You can get it from a torsional moment. Those are pretty much the only two ways that we've talked about in this class of getting shear stress. I mean, you can get it also if you rotate the element by a certain amount, right? You know, you can get it that way, but in terms of these just types of loadings, this is how we get these different.
Right, so, but just my hang up right now is associating the different loadings with X, Y, Z for the Mohr circle.
So first, whoa, okay, so.
That's my hang up right now. We need
No, so for more, yeah. So what you have to do is you have to go through.
Yeah, just do all that, and
then, once we have, you won't have directly these diagrams, you should not have a problem, probably not gonna have a problem that has, I guess it's possible, but we're typically dealing with 2.5D problems, so you're gonna have like a sigma x, a sigma y, and a tau xy, alright? Or you have a sigma y, a sigma z, and a tau yz, right? We're drawing a planar diagram, alright, for in-plane stresses, then we're going to go about doing Mohr circle. Okay, so before we even get to drawing Mohr circle out, right, we gotta figure out very methodically which stresses do we have, or how are they relevant to the bending moments, or the shear force, right? Or it's a twisting problem, so what's the torque? Or it's an axial loading problem, so it's normal force. Or it's a pressure vessel. So then you get the stresses in two directions, well, because of those, because of the internal pressure, right? So those are, so it's this, right? So before you get into all these different things.
that's how Mohr circle.
Okay, alright, oh, okay, yes, okay. So break it down and look at each contribution from each one. So let's just do that. Go through each one. All right.
Yeah.
And so pick your geometry. Which one are you working on? The problem that you're working on. Let's take a look at it.
So,
It is. Pull the. Yes. It's.
this is this one. What? Okay, I'll try to read it.
Okay.
Yes.
All right.
Here.
Okay. So. Okay. So which one do you want to pick? You tell me which.
Start with
those.
X.
Huh?
Start off with X. Say.
What else?
That one.
PX?
Yes.
Okay. All right. So what is it doing?
Doing a bending.
Okay. And what is the bending moment look like? And which axis?
Around the y-axis, right?
Good. And what's the length of action?
Well, that's the, yes, it's px, no, times the px and p.
What you just said was, we're doing the PX.
Yes.
Okay, so we're doing, so write that down.
Yes, times p, right?
Yes, so that's,
So we call that just m,
I would call it,
or mx or something.
you could call it NPX, whatever you wanna call it,
Okay.
but it's, and this is why you would draw the circle, right?
Yes.
And so we're trying to identify the contributions.
Yeah, so it's right.
I would just do like, okay, contribution, like even in what I wrote, I said contributions from PX.
Yes, so point is, don't do this, do 3 circles.
Sure, do 3 circles if you want, yeah, okay. So that one is contributing, yes, a bending moment, right?
It's also a shear force too, I think. No,
So PX,
right, there's no x, isn't there?
so if I move it, yes, that's exactly right. So if I were to move it over to here, right, it'd just be a normal
Right.
axial force, right? So it's also contributing a normal stress, right, in the x direction of px divided by the cross-sectional area. So that is everything that px.
Just so, assume it's actually kind of right, not for you, but.
Say that.
So,
No, No, what, just say it again.
Sigma the, here, this is, not that, this is n, not, this p is normal force.
Right.
Okay, this is incorrect.
What is incorrect?
V over n.
Yeah, that would not be, typically we don't use that as a.
Okay.
Okay, alright. But you haven't written anything down.
Yeah, I know.
I'm very confused about what's going on here.
This is the numbers, this is all just, okay, and I'm doing this diagram here, and I'm not actually start writing things down, so I'm out of there yet. So, X, we have this, and that, and sigma. And for Y, we have,
Just write down contributions from PX.
yes,
On your paper.
Here.
Contributions, no, write the word contributions from
And
PX.
words?
Yes, and words.
okay,
Yes.
just do PX is this and this.
I think we should.
Run it again.
Draw one circle and write, first write contributions from PX, right?
Does that work?
Do whatever you want.
I mean, I don't exactly what I tell you is, but I'm going on paper, I'm writing down, I guess. This works for me. I'm seeing things I'm gonna write down, that's what
I'm just trying to organize things, help organize things.
okay.
And if you want to do it a different way, so go ahead.
Just to clarify, there's no transverse shear from PC because it's like acting on no area on A, right? Just circle. Is that what you mean by A equals 0?
Okay, so in this case, we're looking at the contribution of PZ, right? Okay. There is, yes, a shear force, we agreed, right?
Yeah.
If I move that over there, there's a shear force, TZ, right?
Yeah.
Okay. Now, what's the equation for transverse shear?
There's a V over A, and there's dQ over IT.
Right, so if we're looking for transverse shear, right, VQ over IT, right? And Q, right, is dependent on its A prime, right? Remember, so if it's like the opposite, we were just talking about bending stresses, right? Remember, bending stresses are maximum at the outskirts, the top and the bottom, okay? And the transverse shear stresses are just the opposite.
I'm past it. You're under
So the
not
transverse shear stresses are going to be 0 if you're at the top or the bottom, because A prime is equal to 0. Right, there's no area over which it's acting, okay? So since there's no area over which it's acting, then it's equal to 0.
Okay, I got it.
Okay. Alright.
He's complaining about some math class he had to take.
And so that's all I have there with that.
He came in for later. No, look, he has to take, he was complaining.
Oh, and there's those letters.
Yeah.
I was literally feeling like, dude. I was a number of maths. Just say that. Honestly, you know there's other people in this class.
I just can't believe he actually did all say it's literally energy on number math. There's no numbers. Dude, you took it all. You're not taking an engineering level. And you got a C on the fast. Really
session 21.
Hmm?
Right, is due on Thursday.
Yeah, tomorrow's Wednesday, yes, so that's due on Thursday.
If we redo old homework problems, is it gonna give us a 0?
No, he said this 20 million times. You're doing it 25%.
No, I mean like that we already did, like if we do them again.
Oh yeah, don't do that,
Oh, okay.
don't do that, it will give you the penalty. If you've
Oh.
already done them, yeah, don't do that, the way it's set up is that if you go back and you do them, right, if you resubmit them, it's going to,
It won't use the highest score.
Well, I think because it overrides your grade.
yeah, it
if you
overrides,
score
cause
as
it
bad
says it says it was turned in late, that's just the way
Doesn't just go with the high score from earlier?
it does it.
It
That's
doesn't.
just so
And I think if you look on the Canvas forums, maybe it's a setting, I don't understand all the intricacies of how Canvas does things, but this is, yeah, so beware. Beware.
Yes.
I won't be that. It's the one where he's in the fifth box. He was like, go around. Where's Nate? And then I go keep it. He's like, yes. He's like, that cost a fucking baby. And he goes, oh, yeah. And then like, I don't know what I'll go up with one.
Was it him?
What's it called? I forget, look up, yeah, I think you should
Did you watch the season? Yeah. No, I know. I didn't see it all. But you've seen some of it. What is it? Fake muscles too.
Because the whole point of the show was, the whole point of the show was like a fake sketch show. Okay.
So it is.
You made it work. The whole point of it's like a fake rank show. Right? He's gonna walk around and then
His humor is really funny.
I mean, only 50 best part.
Which one? What is that?
You didn't see driving Burger? He just drives around with a decal, like a fake cat. And they fix it up there. And he's like driving around with a and then he goes, like, it's the outside. It's like, no, go.
It was nice because this thing was the same stress, only just that.
And he has, it's like,
That's your stress back.
the
And then, like, so for each and three, it's
Right, dude, what is-
and then obviously your stress, your stress. And then, like, half is the shear, which is something the oldest, this is part before the Mohr circuit, this equation, which is, actually, no, this is just raised the Mohr circuit.
Calling it.
So, you don't want stress and that. stress
you wanna,
is.
you have a question?
I think that is.
Okay, so,
Here.
That's just.
okay, so let's.
So
I agree. It's giving a moment,
let's see what.
okay?
You give me your. Well, I'm gonna say like, hey, my online class is 6 as well.
Right, so this is just,
But,
because actually I'll call you after and I'll, I'm going to be doing, keeping that in line, So, now, the last part of
It's not twenty, or so.
basically.
Is that all, oh, yeah, that is something.
Yeah.
Is
Which one?
That's.
Yeah, that one is basically.
Sorry.
I have why.
There's two other ones, so like. This equation, the shear, I think the stress, and then it's
Yeah. I guess,
Fair enough.
Okay, so that'll,
Okay.
so that'll be just,
So it's over.
Yeah, that is the same shape.
Almost around, almost around what?
Yeah.
the moment is about y.
No, that's, almost that one.
And
Yeah, it's these two.
it's
You
given
want these
by-
two, and then you find the more radius.
What does I
Yeah,
stand
it's
for?
going to be.
I is, I don't know.
oh, it's right there.
Yeah, I don't know, I don't know.
Here, for
And then,
y,
so then once you get that,
y.
so it's right, and then you find this, that's,
Yeah.
Yes, there's
So
also.
you put in the more circle and find that radius.
but don't you have to find, like,
Then.
isn't this
for
shear,
y,
which one, like, the two stresses?
Or-
Just find it.
You only need
So
only
before
one
you
stress.
start,
Because if this, you're going zero, so it's gonna be just
Oh,
that
okay,
stress
okay.
over 2 squared
So
plus
this
the
is-
shear squared.
Right, you
Oh.
have that normal stress, gives it, because if you're thinking about it.
Well, not the shear, just
Right?
this one.
And
The
this
stress
is
divided by 2
right.
squared.
I think the question that is that stress.
I mean, you're getting for these actually.
Yeah.
Well,
It's a little more easier for that.
Yeah, it is a sigma.
Just so you pointed out
Opposite or negative.
Yeah.
Alright, thank you.
It is a negative, and again.
There's a whole iPad got, to me, getting an iPad just for writing notes instead of this.
Okay,
It's like, it's a lot better.
so, for me, so we're,
Right hand rule.
I got
is
this
good,
for
but
250.
remember that.
Oh.
Sigma is equal to negative m.
but like, this isn't only 250.
So it's not.
Because I
just
know a
about
guy,
what
knows a guy that like,
it's
their
where
insurance
it
company
is.
uses them for free, and they just give them like insurance company, sell them.
This side of.
But like, so like for me, it was worth it.
This side of the-
I don't know if I pay $1,000.
That was,
Then it's like 1,000 for basically.
Yeah. I mean, like, this is also like older now, so you
So-
can probably get it for like, I don't know, like 600.
What's interesting here.
It's 600 for basic.
But
Yeah.
yes, it's actually.
It is nice though.
I use my computer reader, but I don't like, I don't like pen.
Normally.
It's right.
You have a Windows computer, right?
Huh?
You have a, it's a Windows.
Yeah,
At
computer.
the same time.
I would
There's-
use touchscreen. Does it fold all the way over?
A normal bending
Oh,
stress.
So I can't, like, from other side, like, from other, I haven't even class
Yeah.
with this.
So write
So I would
that
draw
out,
the
so
shape
write
here.
sigma x.
Look at it, I'm like, damn, I wish I did another class, so like, I don't wanna sit there drawing like a thing, cause it means screens and all that, I can't fit it, so.
I had a Windows computer that folded all the way over, and honestly, like, it worked really well, like, before I got this. I mean, this is better.
Yeah, so it's like,
And then
the
this
board
is-
pack,
yeah,
like, you see and bring your notes and the.
Yeah, you
the-
have.
Yeah,
they're all
it's
seen in IR, but
But I'll probably figure something out.
So that one is kind of.
Yeah.
Alright.
Gotta make sure you go in.
Now move on to our next one.
Yeah, so actually, that case, they can even have one note running on it. I don't wanna get one that is like, oh yeah, you knocked off or something.
No, Windows pretty good.
Yeah, one note is good.
And.
Cause like the other ones you have to pay for, I'm not trying to pay for it.
Yeah, I'm not trying to do that for dog.
Yeah.
Like just to like write stuff.
Yeah, just like,
Not where,
right?
That's, yeah.
Well, I mean, we're gonna end up writing much stress, so I would write,
What?
how, and I would write how.
Yes, that's what I wrote about, to get per.
That's here. These typically used, right? So I would write how v, there.
That's Matt, I agree. Matt, I agree.
Okay, now what else? is,
And which, yeah,
and which direction is that acting?
you guys up?
Huh?
It's positive, right?
Well, just forget positive,
Well,
negative,
example,
which direction is it acting? Again, you're applying a torque this direction, you're now on this side, so it's gonna be going down. So I would write tau T.
Oh, there's that.
Yeah.
Okay. So,
That's tau sub T going down.
Here.
Mhm. Alright? And those are the two contributions.
there's no one.
So, not at A.
Yeah, okay.
There's a moment on this, that's why you had to write where it's happening.
I see. Because, I mean, there's movement here, yes. More, I mean, because it's pulling the whole thing up, bending, right?
Okay, so, yeah, you're right, there is a moment, okay, and it's about the Z direction, right?
Right.
And it's causing, you're right, it's causing this to happen, right?
Mhm.
But where is this located? It's located on the neutral axis. We just wrote that my over I, right? And if y is equal to 0, then there's no contribution to that stress.
A is on, so what do you mean A is on neutral axis?
So we should go back to section 16. Go down. No, go down. So these are the contributions from Py.
Mhm.
So yes, we identified tau T, right? That was from torque. Tau V is, like we said, it's the bending, it's a transverse shear stress. And then there's no bending stress because look, it wants to bend, right? This is, imagine you move Py over here, right? That would be causing this to bend like this,
Right.
right? And if it's causing it to bend like that, and this is on the neutral axis, there's no bending stress.
Is it on the neutral axis? I mean,
It is.
it on this line or on the side?
It's on the side, right?
Right,
They're
so
all on the
neutral
side.
axis, neutral axis,
They're on the side.
neutral axis, it's more neutral plane than really just an axis.
Sure, yes.
Okay, I see it.
It's on,
Okay, well then.
but it depends on how you
Look at it, I guess.
look at it. Sometimes neutral axis is across, sometimes it's, it's usually across actually.
Okay,
But, it can be, you have a longitudinal axis as well.
point being it's bending around this line, essentially, not just around that point.
That's right.
Okay.
So no bending
So then-
stress. There is a bending moment, you're right. There's an internal bending moment, right? And that's gonna be given by Py,
That was your
right,
topic?
times A.
Yeah,
Okay, but the bending stress is 0.
okay. So then it's gonna be tau V, so tau Y, tau V minus tau T.
Yeah. At least if, I mean, that's for that stress, right? And so if we're looking at that face, right, it's a little bit confusing because, like if you go scroll down, right, to the next slide, right?
Yeah.
We say, these are the contributions from Py, right? And, this is gonna be tau xy. So that's also a little bit confusing, right? So we're looking at the x. So if you look at, you draw this, right? Tau xy should be positive. The x is coming out of the beam, right?
Yeah.
So yes, so tau v, right, is contributing positive tau xy. Tau t, as we're calling it, is contributing minus.
Let's see.
Okay. So you see that's what you have, tau xy, it's, this one is from the transverse shear stress.
Yeah.
This one is from torque.
Okay. Then Z. Here we do have movement. Right?
Yes, we do have a moment, and is it gonna be causing it to be in tension or compression?
Tension doesn't have a thing.
That's right,
Right.
that's a tensile stress, right?
PZA. Is the movement, right?
Yes, I actually, can you go back to my diagram, because I just wanna make sure, yes, it's PZ times A.
That's about the axis, right?
And that will be a negative, negative my over I, right, but it's gonna be a tensile.
Right, so is it this?
Oh, no, wait, are we doing PZ?
Yes.
Yeah, PZ's into the board. Like up
Well,
here.
yeah, I mean, apply negatives later. I'm just listening to say, I'm doing the passive for now. Apply negatives later. That's it. Does it make any sense? No?
Again,
Okay.
it's easier to think about what the deformation is,
Okay, fine,
right?
sure.
If you use, as I'm like, what?
Change direction, okay, fine.
Right. For all the problem as it is, right?
Fine, fair enough. Okay, sure.
Alright,
So then,
so that means that it's gonna, so if I'm applying a moment this way, right, that means it's gonna put it in compression on the top, right? So it's gonna be a negative.
okay, so. Well, that's not true, but because the tau's not just M, it's more than that. But,
There's no tau.
yeah, right, it's sigma actually.
Well, I mean, there's, okay, so
Well, there's tau for
there's
V.
tau because
There's
of
also
V,
V,
right? But for this, we're talking about the bending stress, right?
Yeah.
Sorry.
Yes.
Yes, so then PZ, right, is, yes, the shear force, right?
Mhm.
But then there's no transverse shear stress because it's at the top of that cross section. Right, if you were looking at it, if you just, how do I put this? If you look at, okay, I have a shear force, right, and when we take a cross section, right, and you're looking at, okay, how do I calculate the transverse shear stress?
Mhm.
There's no area for it to work on.
It's sitting on the.
It's on the
And that's the
top.
circle essentially. You see.
Yes. So there's no transverse shear stress because of PZ at that particular location.
Okay.
And that's
So
those
sigma,
are all
so
the,
sigma z can be negative, sigma summum essentially.
it's gonna be negative PZ
Yes.
times A
Over,
I
okay. Well,
times
times C,
C.
oh, right.